yellow chalk. Use the yellow chalk. Use the yellow chalk.
Yellow chalk.
The white chalk is blue.
Yeah, today briefly I want to discuss different notions of solutions we use while trying to solve PDEs or solve PDEs or some other versions of some equations. And the main goal of this talk I want to is like convey the idea of trying to if you can't do something explicitly, you have to think how to move to a different place, like different space rather, so that you can where you have more freedom than the the conventional space that you're working in. And this idea is true like many of the times you must have heard like I think it's Poincare or something who said and I'm not sure, but mathematics is the art of trying to find how to define the same thing in a different way. So in the same sense, like it is a normal it's a normal technique in algebra. It's very common in algebra where they have rigorous notions of it. Here I don't have it's rigorous, but it's not the same concept of duality as I said. Like it's not the solutions won't be a dual of something or a dual of some object in some sense. It's just that notion is what I want to show, that it's also used in analysis. So the most basic example is in finite dimensional vector space, I want to show the vector v is 0. There are finite dimensional space, it has an inner product. So how do you do it? Not how do you do it. What's the equivalent statement to this one? Suppose a vector is 0 and this is an inner product space. What is the equivalent way to say that? Equivalent something is 0. An inner product space.
VW is 0 for all.
Yeah, that's all. Right. Space so functional analysis is based on this idea. In the sense it was developed because this is true in the finite dimensional case. So in functional analysis, now it's an independent subject of its own. But when it was being developed, it was for trying to show existence of certain PD, mainly linear PD. So the simplest PD I will take. Why I'm saying PD is because ODEs you have certain existence theorems when they're nice enough, so you don't need to. Like existence is not hard in ODE case. I mean it's hard, but it's been shown. PD we don't have that kind of a result. So the simplest PD that one first encounters is the Laplacian. It comes up everywhere, but I'll take it in 3 dimensions. So it's like this is your PD, like this is the Laplacian, and you want to solve, suppose, something like this. I have to mention a lot of things where F belongs, where U belongs, all those things. But for now, for the whole talk, I'll keep it vague because that's not needed. So one way, so now I want to solve this, and I want to not solve this. I want to show that some U exists such that this happens. And because it's Laplacian, it's easy. So suppose it's some linear functional. Okay, I'll just set it up. I don't want to write LP things, but let it be LP. For people who are not familiar with it, just some vector space. This is a vector space of function. This is a vector space of functions. and my PD takes this to this. It's like a linear operator for now. It's like a linear operator. So now I want to now I want to show existence of this basically. Some u such that this is satisfied. It's visible right everywhere. Anything if you want to ask if it's not clear, just ask. So I want to do this LU equals F, and the thing is when I go to the LU equals F also means LU minus F is 0, right? And you also have, so I should be able to say LU minus F G is 0. Okay, I should mention this. So the inner product is something like if F and G are, so okay, there are too many. It's this integral in this case, but yeah. So this is true. This is true if these things happen. So now the thing is, for each fixed G, I can view this operator as a functional. For each fixed G, I can view this operator as a functional, right? And one of the tricks that you use so people noticed this and they wanted to show existence. So in this case, everyone knows Ree's representation theorem, right? For the finite dimensional thing. In the sense, every functional from a vector space can be written as a dot product with I'll write it down. So this is a theorem. Functional is clear, right? Everyone knows functional. Yeah. Or you have to, there exists a U such that this happens is what the statement is. But this sort of theorem is true even in infinite dimensional spaces. In some like it has to have some conditions, but it's true in infinite dimensional spaces. So okay, people initially Hilbert and then people wanted to do this kind of argument in the infinite dimensional case where so spaces of functions also is a vector space, as you would have seen in your ALA course, and that's why people started developing the functional analysis kind of arguments. And so a PD generally it's like a mixture of partial derivatives. So one of the tricks that we have in analysis is changing of integration. Like you can do this. F and G are compactly supported, and this integration is for whole of R. Or yeah, I'll keep it in R. Rn, yeah, doesn't matter. But for now, F and G are compactly supported, so the error term is not there. This is just your normal integration by parts argument. So now the nice thing is, okay, now I have this, and so the condition is what? So I'll go back to the Laplacian because I can write it. So uxx plus uyy plus uzz equals some f, suppose. So I can do, I'll erase this f for now. So the dot product of, now for now just assume u is nice, like u is second differentiable, all that, so that this is well defined. This thing into again something which is second differentiable, integral. I'll look at this integral and doing this kind of a manipulation. So whatever derivative I have on u will go on g. Is that clear? Like whatever derivative I have on f, sorry, g star here, it goes to g goes to f here. And same thing I will do, all ux's are there, same repeated iterations, I'll change from u to it going to g. And in this whole process, I have assumed u and g to be in like a nice class of like the C2 functions. And people who, okay, this won't be clear to other like not first years or whatever, but for people who have seen functional analysis or just like measure theory or something, you know that C2 or like C functions, you can't give it a Hilbert space structure. Like there is no norm you can give, no more than like there is no Banach space structure you can give to a C2 function such that it becomes Hilbert, because the closure of C2 functions will end up being L2. So in that sense, it won't be a Banach space, because Banach space, complete, all that things are there. So we cannot use this argument if we fixate ourselves in L2. So we have to start in L2. So we define it as, we define the operator, instead of acting on u, it acts in a dual way. Like I will look at it as a functional, in the sense for each fixed g, I will look at it as a functional, in the sense. So I was saying L u comma g, right, which is the integral. L u comma this is the integral. So I'll shift all the derivatives to g and define the operator or define the functional as u something something inner product. And because this is f, this has to be equal to f times g for all g. If it's true, then I'll call it a weak solution.
So we finding a solution f is that it's true for every.
So this is, so Lu should be equal to f, right? So this should be equal to fg in the classical sense. But now I've changed the definition, so I'll call it a solution if this happens. So that's the functional analysis way to do things. And why we are doing this is, now once I have translated the should I erase or not? I didn't write in. I'll write it again. The main whole this circus I'm doing only to use Rees representation theorem, because Rees representation gives me an element for which it's true, and it also, the other thing is, it's for any f that will I should be able to find a function. So that's why this notion is used for linear PD. Linear PD existence is directly from this argument. So you don't need to worry much about, in the sense, existence of weak solutions is from this argument. So weak solution is something, so classically, if Lu equals f, then Lu comma g should be equal to f comma g, and so u comma the change of integration whatever g should be equal to f. Now I take this as my definition, and I have to find the element u. So you look at this operator as a functional, and U is coming from representation, and this is the linear PDE case, and this is how we do it for linear. So you can ask, okay, U can be anything in L2, right? You can be anything in L2. So and it can be anything in L2. There is, like, I can cook up some horrendous PDE for where U will be the solution. Like whatever horrendous thing in L2, it will be a solution. But the thing is, if my L is nice enough, my job is to show that U also should be nice enough. This weak notion of solution, then my theory is correct. Like correct in a sense, applicable. If it's not true, and the process of showing the solution U that you get in L2 is actually a nice solution, is actually belonging into some C2 or C2 plus something, that thing is called regularity theory. It's like you have weak solution existence, you're scamming basically here. You're scamming the process by saying, I'll just make it such that I'll force the solution. From there, once I have solution, I'll use the properties of my operator to show that it's nice enough and belongs to a nice class of functions. So if my L is nice enough, I should be able to show U is nice enough, and we are able to do this with this definition, because in some sense this kind of a definition is kind of preserving some sort of structure of the L, and that in that sense the weak solution, it cannot be a very bad one even if L is a very good operator. But yeah, so it's not straightforward. You have to do a lot of calculations based on the operator to show it's regular enough or it's actually a nice enough function. But yeah, so at least we have existence here. So once you, like, if I just look into C2, I don't know how to start, I don't know what to do. I have no theorems, I can't use anything, no tools. Mainly because C2 has no mathematical, like, a good structure. It's just that it's a set, it's a vector space, that's all. There's nothing else. So we want to go to something which has structure and then use some theorem, and once existence is done, then I can use the properties of the operator. So this is the linear case. Any questions on any problems?
What's special about a linear PDE? It's like
Linear PDE because I can make it into a function.
Oh, okay. So like a linear PDE, it's a PDE which I can write as a function.
No, it's a PDE for which this is true.
Okay. It's an operator. Okay.
It's an operator from
L2.
the L2 to L2, and it's a linear operator. That's.
Okay.
I mean, you can define it like this for non-linear operator, but then I can't use these tricks. So.
G also have to be a linear PDE.
What?
Is there any, like, does G also have to be a linear PDE?
No. G is a function. So LU is a function. Once I take LU is a function and G is a function.
What?
So it's a inner product.
You want to get a solution which is true for all G, right?
Yeah.
For all G or like for all?
In the sense, as I started in the beginning, right? This thing kind of.
Yeah.
So this is the thing I'm.
Oh, for all G. Okay.
Yeah.
Any-
Yeah. Any other questions?
So that inner product LUG, after we converted using that change of variables, and we are calling it as a weak solution, so that this is a good enough solution in some sense, but it may not be equal to the classical solution. Like those two things.
So yeah, I understand your thing, but that's what. So whenever we are doing this kind of definitions, one of the main thing, one of the things that you have to have is whenever my solutions is classically defined, it has to coincide with this definition, and it will do that because of this fact. And in general, anytime you are going to generalize something, there's classically something happening and you want to generalize to something else, you want to make sure that whatever generalization you're doing, when I look at that definition in the nicest class, somehow it should coincide. Otherwise, there is no point in. The thing is, this in linear PDE, what happens is because of this. If you remember IISER representation theorem, there is uniqueness also after existence. So you have existence and uniqueness. So if I get something here, and it's also classically defined, They have to be the same.
So yeah, once you've converted it into that dual problem, you get existence using the
Rees
research.
representation, yeah. And in the end, Rees representation theorem somewhat will be using, because it's infinite dimensional, all these things, it will be using, the proof of that will be using Zorn's lemma. And Zorn's lemma, Zorn's lemma, that's not.
No, wait. So why do you call it weak solution and like not a normal solution?
Because it's in L2.
So you.
I can't actually differentiate it. I have to show that I can differentiate it.
Makes sense.
Yeah.
We can, I mean, if it's like defined properly, then it is an actual solution.
Yeah. That, in the sense, it will coincide. It will coincide. Yeah. And I think there was a talk on distributions last time. So in distributions, that's what you're looking into actually. This sort of L2 notion is what some I don't know if I have time for that, but I'll come back to it if I have time later. Yeah. This much is for linear PD. Linear PD I can use functional analysis, which is just high school in general. No, never. It's it's a generalization of vector space theory. So we're full nice. Everything is nice. This you'll learn in your undergraduate course nicely. They'll teach you properly. But this was hard work done in 1940s, 1950s. But now, like interesting PDEs, which are not linear, are like, you can take example like Navier-Stokes or any Navier-Stokes with viscosity and all these second order. There are a lot of phenomena somehow which obey a second order law, in the sense there's second order and it's also non-linear for, I don't know, for troubling us in some sense, but they are there, and you want to develop notions for these things also. I can't use this theory mainly because linearity is not there, and another thing is this enforcing this kind of a property there will be bad, in the sense the solution itself is not linear, and somehow some manipulation I do to get a solution here, it won't, like, you can't always show it's actually what happens physically. In a sense, it's not respecting the structure of what I'm trying to find the solution of. So again, I'll come back to Laplace. Laplacian is linear, but it's also a second order operator. And there is this guy called Perron, if I like, not Perron and the Perron. So what he observed was, so this was the question. So I have Laplacian, and you say on B1, and u equals to G on B1 complement. Complement is not ready. Just this is boundary value problem. You should have seen this in ODE.
What's B1?
B1 is unit ball in RM. So this you should have seen in ODE or ODE, like ODE things. Not the course. In general, you should have seen the boundary conditions and initial, like it's the same as initial conditions. Not much different. So what he observed was, I look at solutions which are like, I look at functions which are like this. Okay, I have used F, I have used G. H. Put a minus here, that's for certain reasons, but leave that. And H is greater than equal to G, and I'll take infimum of such H at each point, and somehow that turns out to be a solution. some like you need to have nice assumptions on f and g, but it turns out to be a solution. And people saw this, and this kind of so I'll call this a sub solution, not super solution. In a sense, it's above h, and this on the boundary also it's above g. So I'll call this kind of thing a super solution. And people observed that this kind of techniques were like this kind of argument was working well in the non-linear second order PDEs which come up in fluid dynamics, or I don't know, they come up in a lot of things. I'm not an expert, but they come up somewhere and they're interesting. You have to believe it is interesting. And somehow this kind of an argument was working really well. And why this was working well? Because what was happening was this process of like at each point they're taking infimum. It somehow was, I'll come to that, but it was somehow like it's like minimizing your energy, something like that. And they were able to they had some vague arguments why this is working, and they tried to give a definition based on these kind of facts, so that they could again use Perron's method basically to argue the existence and uniqueness of solution. So Perron's method is basically this: you look at these kind of things and you go to infimum and you can prove this is a solution. That's basically Perron's method. And constructing these kind of things is pretty easy because it's not an equality, it's inequality. I can do something in CC infinity functions to do this. I can just use some x power functions to do these kind of things. So once I have this kind of thing, Perron's method is easy. So what people did was they started developing this notion of viscosity solutions. I don't know who started it, but like the legend in the field is like this person called Caffarelli, and currently like there have been a lot of people who won the Fields Medal also working in this area. But viscosity. It's called viscosity now because it is like they first applied it to the Navier-Stokes viscosity thing. Viscosity viscosity solutions, yeah. I have some non-linear second. Okay, give me an example of non-linear second order PDE. Non-linear, yeah. This is linear. Actually, let me write 0. So this is non-linear. You have to believe that it is not linear. Like determinant is not linear, so it's not linear. This why would you consider this to be important? It just says that so suppose this is greater than or equal to 0. It means all your eigenvalues of the Hessian are greater than or equal to 0, and that means your function u is convex. So because each eigenvalue is greater than 0, convex function in n dimension, like convex function in one dimension is this now. Suppose it's second differentiable again. If this is true, your function is convex. So same thing, in each direction you check, that's basically checking in each eigen direction, and if each eigenvalue is greater than 0, this will happen. So it's like a convex, it's a criteria for something to be a convex function. That's why you're interested in this. Convex functions are very nice. Like you can show a lot of things about convex functions. They're like locally Lipschitz, they are second differentiable almost everywhere. All those things are true for convex functions. But anyway, this is a nonlinear PD, and now I want to, and another thing, convex functions, they need not be second differentiable at certain points, right? Like this is a convex function, but it's not second differentiable. But I know for smooth functions this is true. So I want to use this PDE notion even here. because here I have methods. I don't have methods here. This is a random object sitting in some random place. This is a well-defined object. So I want to even include this in this. Like I want to include the rough situations which occur actually. Like rough situations occur actually, not even in this just this case. In physical phenomena, there are points. These things are called blow-ups, and these things actually happen. The millennium problem is for Navier-Stokes that blow-ups happen or not isn't, but like there are many other objects where blow-ups do happen, and it's a physical thing that like blow-ups happen. I want to include that in my formulation of my model. Like this is a PD is basically coming from a physical model, right? You want to incorporate all sort of situations in it. So that's what there are a lot of interesting things that they wanted to include in this formulation. And now, okay, how do I do it? So this was a motivation. I don't know all the motivation. This was a motivation. So I want to say, suppose I want to evaluate this thing. At the point x, right? I want to evaluate this at the point x, but somehow my u is not differentiable. Say it's not differentiable. So how do I do it? So the thing they come up with is, okay, my function is like this. What I will do, I'll do two sorts of things. First, I'll touch it from below. I'll touch it from above by certain nice. Okay, no, this is a bad one. It's not a good example because I can't touch it from above, but I can touch it from below. In the sense, this is not correct. Don't believe me. But what I'm trying to say is, they're gonna make it nice. Like they're gonna approximately make it nice in some sense. Okay, this is bad. So this is coming from above. This is coming. So you can only do coming from below. This is not a correct thing. This is not a correct thing. Mentioning again, this is not a correct thing. But my main thing is, they are going to put a parabola here, which either touches from above or touches from below, right? And once a parabola is there at a point, I know locally it's differentiable. Parabolas are nice, yeah, they're good. So if it is touching from below, I want it to be a super solution. If it's touching from above, I want it to be a sub solution. Basically, in the end, what I'm using is, u is something like lim is greater than 0, and lim sup is less than equal to 0. That will imply u equals 0. That's why when it's touching from below, I want it to be a super solution. When it's coming from above, it has to be a sub solution. And if that is true for all the parabolas that I can attach, such that touches from above, touches from below at this x point, I will say in viscosity sense, this is equal to 0. Any questions? I sped up a bit. Any questions?
You can't do this here.
In a sense, there is no parabola which will come from above. So when that happens, it has to be this, like what you said.
You don't need to.
What is it called? Man, what is that thing called? When the if is not satisfied in a statement.
Vacuum statement.
Yeah. It's vacuously not a super solution, but you have to check if it's a So this is how they defined viscosity solutions. And now attaching parabolas is easy. I just need to look at some radius around that point. I'll attach parabola, and I'll show existence. Depending on now it becomes a parabola. I just need to find a parabola such that this will be greater than equal to 0, greater than whatever. And now I'll do this technique. Infimum of sub solutions, or infimum of super solutions, or supremum of yeah.
Wait, when it's lower than when you're touching it from below, why do you want a super solution?
So infimum of super solutions. Yeah, supremum of sub solutions. Yeah.
Yeah, but when it's starting from below, why do you want a super solution?
So that's what I was arguing, right? So in this case, suppose I have infimum less than equal to 0, but and lim sup greater than 0, I can't conclude anything. But if it's reverse, I can conclude u is 0, because I also have the relation here that this thing is greater than equal to that thing. So that's why you would want that kind of a. So these things are called for. So the notion changes slightly. This is for something called elliptic equations. This kind of notions are there. Parabolic, hyperbolic are also there. The notion changes, like idea is the same. Like the notion changes slightly because they are in parabolic. It's like the heat equation. There's one time parameter, and then everything else is space, and then the time parameter is in just the first order. So you have to change it a bit, but in general, this is the idea. You want to use this Perron's method kind of argument to show uniqueness and existence. Yeah. Any questions? And the thing is, it turns out for convex, I want to, in viscosity sense, if something is convex, then it will satisfy this in the viscosity sense. So like it is including all sort of bad convex examples in the viscosity notion. And in general, it turns out that it is accounting for the roughness that is coming from that should be allowed in the physical phenomena. And yeah, this turns out to be an important definitions, and this definition goes long. Like, so this is all like PDE, right? People discuss things called integral differential operators. These are operators which, so PDEs what they do, they only take local information. In the sense, I only need to know to evaluate at point x, suppose this thing, I just need to know the value of d square u around a neighborhood of x, right? It doesn't care what happens outside of that. But non-local operators or these integral differential operators, they also care about what's happening in the whole space, like whole Rn. They care about those things, and even there in those kind of equations also, this is this turns out to be a good one, like a good notion. Why we care about integral, that I don't have it. It's something you have to should go and ask Anup if someone wants to know. How much time do I have?
As much as you want.
Oh,
There's no limit.
okay.
I mean, unless you.
I mean, I'll discuss.
12
I'll briefly discuss one more, and I think then it should be fine. I'll be done because it become long. So, how many of you? No, everyone here has seen this Euler-Lagrange business, right? In your physics course. Second semester physics. First semester. We didn't see it, but
No, we saw it technically. Vishima didn't do something like I forgot. I think. Yeah.
yeah, the same Euler-Lagrange equation. If you are curious, or like if you wanted to learn it properly in the sense a bit more rigorously, you would have Googled Euler-Lagrange, and after that there will be some guy on YouTube saying calculus of variations, and he would have showed something. All these things everyone has done. So this calculus of variations, of course, again inspired from physics. This Euler-Lagrange or Hamiltonian, all these things. Hamilton, the thing is, he's a mathematician, so I'll not say. But yeah, Euler-Lagrange, it's inspired from physics things, where like basically you're doing some energy minimization. So to some physical law, you're associating some invariant and you're minimizing it. Not invariant, a certain real valued thing, and you're going to minimize it. That's what you do in calculus of variations. In the sense you vary u until you find the minima. That's the idea, right? If you remember, they define something. I don't know. Like Lagrangian is like u minus v.
T.
Yeah, something. T minus v. T minus v.
Tree.
Huh?
Tree. T for tree.
Oh, T for tree. I was like, what is T minus u? But okay. T minus u, and they somewhat differentiate it. Like they take del L by some del something, and in the end they'll say this equal to 0 because it's in minima or something, and then they will show the physical law. Like when this is true, my whatever Newton's equations are true is what they like. That's the idea, right? So same thing. You want to do the same thing, and yeah, you want to do the same thing basically. And if you observe, this is also a different notion of solution. They're like just going back and forth with this full freedom, but it's a weaker notion in the sense. I have a PD, I can associate certain functional to it. So, not functional. I will not say functional. What should I say? To linear PD, it's like a PD. I will associate something which is going to real life. Think energy. It's actually called energy. Like it doesn't matter what it is. They just call energy. Like the PD will be modeling something, some coronavirus, and they'll still call it energy. So let's call it energy. So I have some PD operator L, and corresponding to that there is some E, and E takes your functions, right? Actually functions to real numbers. Right. So this is what energy does, right? Takes functions to real life. Like given some distribution, you can find energy in electrodynamics, not dynamics, statics. You can do that, and this is what here also we are doing the same thing. Given some PD, I associate some energy functions. This and what I will do, I will say that there will be some function u which minimizes E, and if that happens, then it will be a solution to L. So it's called a variational solution because it comes from this calculus of variations ideas. It is called variational solution. And you will ask, oh, in physics you can go back and forth, full you can do. There is not in a sense they can do it, we can't do it. Like it's still a weaker notion. In the sense you are doing something like this set of functions you're looking at is bigger than the set of functions where L is defined, because you want to show minima exists. So showing minima exists, how do you do it in? So you want to show some minima exists. Okay, you want to assume like showing minima exists is. I'll just give you an R2 example. Okay, not R2 example. Okay, I'll just give a real line here. So real line, you have an open set. You can't say minima exists. If you have a closed set, you can say minima exists, right? Closed set, not closed. Compact set, you can say minima exists. That's real analysis. So the same thing is true for these function spaces. If the function spaces behave something like open set, I can't say the minima exists. I have to go to certain space which behaves like a compact set. It's actually not compact. Don't misquote me. This is not. It's about the function space having certain properties so that I can show its minima exists, right? So yeah. So that's what we're going to expand the space where these functions are defined, and we are going to employ some techniques to show minima exists. There's some standard way to do it. So energy minimizers, how do you do it? Because it's going to real line, I get like some. It's in some sense of integral. Like it is some sort of. It looks something like this. You can for people like the senior people, I'll put some measure here so that it actually is like this. And from there are many things you could do, like the same actually, like you could actually use the same proof to show minima exists. One thing you can argue is, suppose the set of functions u am allowing is convex in some sense, and it's a known thing that for convex, like it's something like this, right? And if it has some conditions, so if you know this, if a function is defined on a convex set, then something happens and I can show me. So these things are true, and once that is true, I'll be able to say, okay, it happens because my space is nice, my f is nice, there is some convex, like because of all these convexity arguments, I'll be able to show energy minimizer exists. That is easy to show. Now it's a weaker notion than L, like it's solving L, but I'll call it the variational solution. And as I said again, it has to coincide, right? It has to coincide. That again is not very hard to show, because if LU in the same proof of Euler-Lagrange, if you remember, if LU equals 0, the corresponding energy function, when I differentiate it, this LU term appears, and because it's 0, the whole thing becomes 0, and the derivative is 0, and you will say, okay, it's minima. Right? You have to go to second derivative, but no one does that. It's just call it some sort of extremal. I think I should write it down somewhat. Like, does anyone want to write the Euler-Lagrange thing?
Total time derivative.
Yeah, you take derivative, and then in the end you get LU or like whatever your Newton's equation, and that is 0, and that's why the derivative is 0. If you
I don't know which formula.
no, so I don't know the physics form. That's the problem.
Can you try it, but I might restart.
Sure.
That is fine.
There are physics mediums here as well.
She wants to try, but
Yes, sir.
you can try.
Minimizing the action.
Why not?
The energy function will be the action.
Yeah, just write down whatever you know on the Euler-Lagrange
This
thing.
is the Euler-Lagrange. What do you want from it?
No, just write down whatever you want.
No, a solution to the EL equation will minimize the action in the.
Yeah.
Oh, is it not called energy?
It's action.
No. The proof of this, in a sense,
Show that varying the action to first order gives you this.
You want the derivation of this.
in the derivation of, I don't want, it's fine. Just believe me. In the derivation of this, you will be using something like something is 0 because it's a
Because it's a boundary term.
No.
Not the boundary term. The integral of something will be 0
Yeah.
identically, so the something has to vanish, so you'll get this.
Yeah, exactly.
Which boundary term? I remember the boundary
I'll after the talk I'll go look it
That's
up
just
on
because the
Google and
paths have the same endpoints.
Right.
So
That is the boundary
basically,
term.
because of that thing,
They're
if
not
it's classically
the
0, then
boundary.
it will actually be energy minimizer. It's not a problem. Again, it's a weak notion. Again, you have to do regularity stuff to show things. In that one also, viscosity solutions also, you have to do regularity. Like you have to show it's nice enough. And that's the main part of researching nowadays, like PDEs. If you look at any PDE topic, there are 3 things: existence, uniqueness, regularity. Regularity is because we are doing this kind of scam things, because we are generalizing the notion of solution to make the first 2 parts easier, and the last part is where we are able to handle it, because we have some object to deal with. And that is what I wanted to convey. Like these are the 3 things that I have seen in my whatever projects, courses, and I wanted to just share that these sort of things can, like this sort of ideas of making. So if I can't find a coin in this black square, I'll just say it exists in this room and I'll move, and then I'll like it existence becomes easier, but then again I have to search the whole phone. Yeah, that's that we shift the hardness to some other place, and then we can handle it there. Yeah, that's the main, like that's the whole talk, I think. Any questions?
Are
Anything?
there any conditions on this energy function?
Yeah, everything has to have conditions. If it's bad, it can be bad. That's always true. So in any talk you are saying everything has to have a certain kinds of niceness. Like it can be the most general thing, and so this is optimal is what there has to be some optimal condition, but for just the idea purpose everything is nice. And yeah, it's the problem is for me to define these notions of nice, I have to define objects, like I have to define things what is nice, and that is not easy. Like it's not easy in the sense you guys have not seen it, and it is pointless. Like the talk will just go on defining these new objects, and it is not worth the, like it doesn't give you any idea or whatever. Yeah, any other questions?
Which part of physical representative?
He said something. I don't know. I don't know algebra, so like I can't comment. But if it is, I don't know. So like you have to tell me. Like you have to tell me.
These representation theorem, that is basically some data.
I don't know this. I don't know how is it printed up?
Like that is basically.
Oh yeah, nice. Yeah.
Anything else?
I need some book recommendations for delta epsilon.
Delta epsilon. Oh, analysis. Have you which year are you in? If you come, it's fine. Like don't worry about it, because yeah, like you have to do these things slowly to digest them, in my opinion. But if you actually want some recommendation, what's that book which you guys used? Analysis one.
This is one.
Abbott.
Abbott is a good book. If you don't like Abbott, you can check Rodin. But yeah, it's more than the book. You have to have instructor to give you some motivation and all that. So just wait for it.
Abbott what?
Abbott real analysis. If you look, it should come.
Understanding analysis.
I have not read that book.
That's the book title.
I think I heard people say the same about Algebra.
This is just for like just the third year and above. So this I was last was talking about this variational thing, right? So it turns out a lot of these PDEs that come in geometry end up being of this form, like where they admit an like in geometry, like you should have a curvature minimizing or whatever, some minimizing some flow or something, and these things end up being in those sort of PDEs. But the issue is on like functions on manifolds, they don't have a nice vector space structure or whatever. I should not say vector space. Something they don't have some structure which is applicable to this sort of calculus of variations kind of thing. And people wanted to generalize this, and they made up a theory called global analysis, which is what IISER is doing. Like the Donaldson's work and all that. It started in 1960s with this. Like they wanted to look at PDEs on manifolds, but like the solution techniques weren't working, so they went but then Donaldson came and he's like, I'll just look at that space and then I can say about manifold something. But like that's the start. That was a starting point for this area called global analysis, where you infer about the geometry of the manifold from. So it's like, it's like they wanted to do functional analysis but in nonlinear setting, and you can look it up on Google. I'm not an expert on this. I just have pop knowledge of this, but you can look it up. It's interesting, I think. But
Wait, so you were I don't think I understood everything you said about the viscosity solution thing. Right.
Fair enough.
So did you take there you're not having Laplacian, you're taking some other operator.
I can take Laplacian. That's
You can
not a
take
problem.
Laplacian. You know that's how Perron's method something works, right?
Perron's method